All right. Hi, everyone. My name is Brandon, and tonight I'm going to summarize Stanton et al.'s paper, Does Knowledge Distillation Really Work? Here we go. So to start off, the authors say that with modern architectures, knowledge distillation can lead to students with very different predictions from their teachers, even when the student has the capacity to perfectly match the teacher. And throughout the rest of the paper, the authors will look at two metrics: fidelity, or test agreement, which measures how well the student predictions match the teacher predictions, and generalization, or test accuracy, which measures how well the student predictions match the true labels. And to answer the eponymous question, does knowledge distillation really work? The authors say yes, in the sense that distilled students often have good generalization, but no, in the sense that distilled students often have bad fidelity. So in this paper, the authors will show you that achieving good fidelity is extremely difficult, even with a variety of interventions, and explain why knowledge distillation does not produce high fidelity students for modern architectures and datasets. As a quick reminder, knowledge distillation is a model compression technique whose goal is to distill knowledge from a large teacher model to a smaller student model. And the way that it works is during training, we have both the student and the teacher make some predictions. Then we calculate the distillation loss, which is the sum of the cross-entropy loss between the student predictions and the true labels, and the KL divergence between the teacher predictions and the student predictions. And this distillation loss should encourage the student to learn some internal representations of the teacher. So with all of this background out of the way, let's get into the article. So the first thing the authors do is some simple knowledge distillation experiments. First, they do a self-distillation, which is when the architecture of the student matches the teacher, of Linnet 5 on MNIST. And they find that with enough examples, the student learns to make the same predictions as the teacher, with over 99% top one agreement. And notably, in this case, self-distillation does not improve generalization. And this makes sense based on what we already know about knowledge distillation. So the next thing they do is a self-distillation of ResNet 56 with CIFAR 100, and they find that as the size of the distillation dataset increases, the fidelity increases, but the generalization actually decreases. And then they do a distillation from a three-component ensemble to ResNet 56 with CIFAR 100, and they find that as the size of the distillation dataset increases, both the fidelity and the generalization increase. And these results are kind of all over the place. So what's going on with fidelity and why should we care? And to answer that, the authors make some really good points. For starters, for large teachers and ensembles, which are the most prominent use cases for knowledge distillation, improving fidelity will also improve generalization. And since the goal of knowledge distillation is to transfer the knowledge from a large teacher to a smaller student model, it makes sense that we want the student to match the teacher as much as possible. So what are some of the potential reasons that the authors looked at for why it's hard to get good fidelity? So first, they looked at student capacity, but they found that increasing the student capacity has very little effect on fidelity. Next, they looked at network architecture, but they get similar results with both ResNet and VGG architectures. Then they look at dataset scale and complexity, but they get similar results with both CIFAR 100 and ImageNet. And after that, they look at data domain, but they get similar results with both ImageNet for image classification and the IMDb dataset for sentiment analysis. And finally, they land on two more promising explanations, which are identifiability, which is asking the question of, are we using the right distillation dataset? And optimization, which is looking at the question of, does the student match the teacher on the distillation dataset? So let's start with identifiability. So for identifiability, the authors compare the results of different data augmentations when distilling a 5-component ensemble to ResNet 56 with CIFAR 100. And the authors find that the best augmentations for generalization, mix-up and GAN, are not the best policies for fidelity. And furthermore, the best augmentation for fidelity, which is mix up when the temperature is 4, is only marginally better than the baseline when the temperature is 4. So the authors conclude that the slight improvements to fidelity with extensive augmentations suggests that increasing the support of the distillation dataset can indeed improve distillation fidelity. However, since the benefit is so small compared to logit tempering, which does not modify the support at all, it is very unlikely that identifiability is the primary obstacle to high fidelity. So finally, the authors turn to optimization. So in the previous experiments, we saw that increasing the size of the distillation dataset always increased the fidelity, or the test agreement. But what about the train agreement? Well, the authors found that, actually, as they increased the size of the distillation dataset, the train agreement decreased. Here, the authors conclude that our intuition about how knowledge distillation should work largely hinges on the assumption that after distillation, the student matches the teacher on the distillation set. However, the results presented in this section suggest that, in practice, the optimization method is unable to achieve high fidelity even on the distillation dataset. And the inability to solve the optimization problem undermines distillation. In order to find a student that would match the teacher inputs, we need to at least be able to find a student that would match the teacher on all of the distillation dataset. So finally, the authors propose the distillation loss surface hypothesis, which essentially states that unless we initialize the student with some teacher weights, which are the optimal weights with respect to fidelity during self-distillation, the student will converge to suboptimal weights. And specifically, the authors say that knowledge distillation is unable to converge to optimal student parameters even when we know a solution and give the initialization a small head start in the direction of an optimum. And in order to match the teacher on all inputs, the student has to at least match the teacher on the data used for distillation and achieve a near optimal value of the distillation loss. Furthermore, the suboptimal convergence of knowledge distillation appears to be a consequence of the optimization dynamics specifically, and not simply initialization bias. And in practice, optimization converges to suboptimal solutions, leading to poor distillation fidelity. And at the end of the paper, the authors summarize everything into 4 nice main points for us. So first, good student accuracy does not imply good distillation fidelity, which is what we were just looking at. Second, student fidelity is correlated with calibration when distilling ensembles. So student models with high fidelity are less likely to confidently make wrong predictions. Third, optimization is challenging in knowledge distillation, which we just saw, and even when initialized with some optimal weights, sometimes the optimizer does not find the optimal solution. And finally, there is a trade-off between optimization complexity and distillation data quality. So while increasing the size of the distillation dataset increases the test agreement, it also makes optimizing the train agreement way harder. And that's everything. Thank you so much for listening, and have a good night.